Hi, folks. Part of this thing that you've been assigned to read is actually really easy to read and very understandable, but once it gets into the actual analyzing of the graphs, some students tend to get a little bit lost. So hoping that this video will help you with that. The beginning, in fact, I think it's the first 7 pages of this, really just goes into how to make good data tables, how to control an experiment, and then some good graphing tips. So I'm not going to stress that too much. I would like to talk about independent versus dependent variables. Just the name of them kind of suggests that one depends on the other, independent versus dependent. It is sometimes very difficult, and you'll see this as we go through the course. It is difficult to say which one really does depend on the other. Sometimes they're sort of interdependent. So I don't want you to get too stressed about which one is the independent, which one is the dependent. Sometimes you'll even be able to make the case that the one that you're calling dependent is the one that you're actually changing. So don't get too bogged down in these terms. Even if you do everything in this backwards, if you call the dependent variable the independent variable or vice versa, you're going to end up with the exact same relationship. The whole point of this entire process is to give you a way to take some raw data in a table, graph that raw data, and then use the graphs that you make to come up with an equation, an algebraic model of the data. So what I'm going to go ahead and do is flip right on over to the 8th page. Actually, I'll stop here at the 7th page. All throughout the first 6 pages, they're talking about this pendulum experiment where a pendulum is swinging back and forth and takes a certain amount of time to swing back and forth. And they call the time it takes to make one full swing back and forth the period. And what they change during the experiment is the mass of the pendulum. So maybe I have one here of 20 grams, 40 grams, 60 grams, 80 grams. And then they plot it. So they're going to kind of start by discussing this relationship that they've spent 6 pages talking about. So when you make a graph, excuse me, in this course anyways, I'm not saying that in the world these are the only graphs that exist, you're probably going to get one of these shapes, okay? And there are really only 6 shapes. You might get a horizontal line, a line with an intercept, a line without an intercept. You might get half of an upward opening parabola. You might get half of a sideways opening parabola, or you might get something that looks like this, like an inverse graph. And the rest of the reading from page 8 on actually goes into, all right, if you get each shape, what would you actually do to analyze these shapes? So the first one is, maybe you get a graph that looks like this. It's a horizontal line. You plot whatever's on this axis versus whatever's on this axis, and it's just horizontal. Well, this was in reference to this data. Keep that in mind. This is called no relation. In other words, I tested one mass, I found a certain period. I doubled the mass, the period did not change. I tripled the mass, the period did not change. No matter what mass I use, this variable, the period, doesn't change. So there is no relation between these variables. And that's a possible outcome. Whenever we do an experiment, we always say, what is the relationship, if any, Witriab, between? So this is an instance where there is no relation. Well, how would you go about doing this? How would you go about coming up with an equation for this graph? So looking back, this is the graph. Period is over here, measured in seconds. This is the unit. Period is the quantity. Mass is the quantity. Kilograms is the unit. So let's look at what they do. First thing they do, they come up with a letter to mean each variable. You don't have to write the word period every time. You can just use a P. You don't have to write the word mass. You can just use an M. Second step, this is just stating some basic algebra. Any line on any graph can be written in the generic form of y equals mx plus b. Third step, they're just substituting some different letters in here. In this case, we don't have a y-axis, we have a p-axis, or period. We don't have an x-axis, we have an m-axis for mass. So they just substituted p in for y, m in for x. Now you're going to notice slope in math was always the lowercase m that was used for it. In science, since lowercase m almost always means mass, we don't say that the slope of a graph is little m. We call it k for constant. So keep that in mind. This m is not that m. This m was substituted in for the x. This k is the constant, the slope. And b, we can still use b because that's the intercept. Now this next step, they're just saying that the slope, k, is going to be the change in the p-axis, that would be the rise, over the change in the m-axis, that would be the run. Now you have to have chosen a couple of points to use. These do not need to be measured points. These were their measured points. Any points on the line would suffice, so pick a couple that are really easy to read, maybe lines that, or where the line crosses the grid. And they did that. They picked a couple of points. Change in period would be the second period minus the first period over the change in mass, and those are the mass values that go with those. So find the slope, just like you've been finding slopes in math. Keep in mind, this is science. Almost always the slope is going to have units, folks. Period is measured in seconds. Those need to be in the slope calculation. You'll see why. Mass is measured in kilograms here. Now, when you divide out, you're going to get 0 because the numerator is 0. This is a graph that had no slope. This is the y-intercept, just read from the graph, right there, saying it's 1.56 seconds. And this is substituting in the slope, which was 0. This is m, meaning mass, not slope. And this is the y-intercept, or in our case, it's not a y-intercept, it's a p-intercept. So, final equation is this. From this generic form, this is all that's left in the end. That is the equation that describes this graph. Now, you may get a linear relationship that is not a horizontal line. Here's 3 different linear relationships you could possibly see. I actually want to talk about this guy first. If you ever get a graph that shows a straight line coming out of the origin, that's a really special kind of relationship. It's easy to describe. It's called a direct proportion. And what it means for 2 things to be proportional is simple. In this case, this amount of mass produces this amount of stretch. Well, if you double the mass, so 2 units of mass, what has happened to the stretch? If you double the mass and you end up 2 doubling the stretch, that means it's a direct proportion. 3 units of mass would produce 3 units of stretch. So that's a direct proportion. We like those. If you ever get a direct proportion, your job is going to be pretty easy when you go to write the equation. This is not a proportion, even though this is linear. Let me show you why. In this case, 1 unit of mass produces this amount of stretch. If I double the mass, boom, look. I have not doubled the stretch if I double the mass in this case. This was the stretch that went with 1 unit of mass, right here, and 2 units of mass makes this amount of stretch. Now, that's not doubling it, so this is not a proportion. All linear graphs do not show proportions, only linear graphs that come from the origin. Now, if 2 variables are proportional, here's a symbol. You guys know what the equals to symbol looks like. This means is proportional to. So if you get a graph that's like this, you can write a statement that says stretch is proportional to mass. We're not going to talk about this kind of graph today. So if you get a graph that looks like this would be linear, not from the origin though. That's not a proportion. Still, we can write an equation for it. So you can read through the experiment here. They put some different masses on a spring and it's stretched by different amounts. And this is the data that they collected. And this is the graph they made. So in this case, they're considering mass to be the independent and stretch to be the dependent variable. Units, quantities. Unit, quantity. So, step 1, just define your variables. Step 2, generic equation, math class for a line. Step 3, substitute. We don't have a y-axis, we have an s-axis. M is the slope, but we don't like using little m for slope in science, so we're going to call the slope k. We don't have an x-axis, we have a m-axis. B is the intercept. Next step, define the slope. The slope in this case is going to be the change in stretch, that would be the rise, over the change in mass, that would be the run. And then they actually picked a couple of points, put them in, and found the slope. So here's the points they chose. And they just chose some fairly easy to read points. So this would be the rise. This would be the run. So this is change in S, and this is change in M. So this point right here would have the coordinates M1, comma, S1, and this would be M2, comma, S2. Okay? And they just plug in the values with units. Okay? Got to have units in your slope. This is science class. And then they found that the slope, K, is equal to this many centimeters per gram. You're going to see in a minute why these units are important to keep. The intercept, read directly off the graph, is this. There's going to be some estimation in doing this. And here's their final equation. So this was sort of generic. S equals, here's the slope. That's K, the slope. M, since we don't have an x-axis, we have an m-axis. This is like our x. Plus, this is B. So, y equals slope times the x plus the intercept. That's all it is. Now, you can always test this. You can tell if you did this right with a quick, easy test. Let me show you. The whole point of this was to come up with an equation that describes the relationship on the graph. So S equals 0.30 centimeters per gram times the mass plus 3.2 centimeters. If this works, if you did a good job, you should be able to go back up to your data. You should be able to pick a mass, plug it into this, cancel, do your math, and come up with the correct or really close stretch. So let's just pick one. In fact, I'm going to pick 40. So what if we put in 0.30, 40 grams for M, and do the math. So 0.3 times 40 is going to be 12. Plus 3.2. So S equals 12 centimeters. Look what happened to the grams. See why you have to include your units? Plus another 3.2 centimeters. gives us 15.2 centimeters. So if we did a good job, this should be the stretch. Pretty darn close. It's a great check for yourself. Units, they have to be in the slope. Units, they have to be on a y-intercept. Common mistake I see. Students want to write this equation out like this, and they want to put units on the variable s and m. You don't need to do that. The only thing that should have units in your equation would be a slope or an intercept. It's assumed that if you put a mass in this case, it's going to have grams attached to it like I did here. And if you do that, put in the right number and units here, cancel everything, you're going to get the right unit to come out of the other end. Great check for yourself. Okay, direct proportion. Very similar analysis. So here's another kind of similar looking graph. This is a direct proportion. Doubling the mass doubles the stretch, tripling triples, etc. A little bit shorter looking analysis. Here's why. Step 1, define the variables. Step 2, this graph is y equals mx plus b in math class. Remember, we're going to use k for the slope in science class. Since the intercept is 0, this turns into y equals some constant, the slope, times x. So you're going to see in the analysis here, they just skip over the whole y equals mx plus b part and say stretch is proportional to mass. So stretch must equal k times the mass. K is the slope. So here's y equals the slope times x, plus b has been omitted. Step 4, they're just finding the slope. You got to pick 2 points. And you're going to see they didn't actually pick 2 points on here. This was generated by a computer, so the computer found the slope for them. The computer did not, however, put units on the slope. So the units would be centimeters per gram. cm per gram. And here's the final equation. Once again, I could take one of these masses, put it in, do the math, find the stretch, compare it with the one on here. It would be a good check for myself. So that's a direct proportion. Square relations. So what if you get a graph and it is not linear? There are three types of nonlinear graphs. These are both square relations. And this last guy is different. So here's an experiment they did. They took a ball, they let it roll down a ramp, and they determined at 0 seconds it was at 0 position. At 1 second it was 3.1 centimeters down the ramp. At 2 seconds, ooh, look at this, 12.2 centimeters down the ramp. At 3 seconds, 27 centimeters down the ramp. So if you plot the data, they said position is the dependent, time is the independent. You're going to notice this is not a proportion. Look at this. At 2 seconds, the ball had a position of 12.2. Well, what if we double the time? It took 2 seconds to go 12.2. What if we double the time to 4 seconds? Does that simply double the position? No, not at all. In fact, you're going to notice doubling the time made for approximately 4 times the position. So 12 times 4 is like 48. So this is definitely not a direct proportion. This kind of looks like a squared proportion. So as the times go on, the positions are really increasing at a bigger and bigger rate. You can't write an equation for this because there's no line. There's no y equals mx plus b that we could apply to this. This would be the kind of the generic equation for a parabola that you're used to from math class. So before we go writing an equation for this, you've got to do what's called linearizing the graph. Now, since on the original graph, the positions were really blowing up as time went on, you could make the argument that the time axis isn't keeping up with the position axis. It's not increasing as fast as the position axis is. So a way that you could actually make the time axis increase more quickly is by squaring all of the times. So they added a column to the data table, and that column's called time squared. And if you take time squared, you're going to end up with seconds times seconds, or seconds squared for units. So this column is simply the first column, everything in it is squared. 0 seconds squared is 0 seconds squared. 1 second square it is 1 second squared. 2 seconds square the quantity, you're going to get 4 seconds squared. And you're going to plot a new graph. This is called a test plot, they're calling it. They're plotting, instead of the original one, look at it, it was position versus time. This next one is position versus time squared. Okay? They took all the times, squared them. Look at the units, are seconds squared now. Whatever you do to the quantities, you have to do to the units. And look, linear as can be. So we can say this. We can say that position x, they're using x for position, is proportional to time squared. Something to watch out for here, folks. Normally in math, the x-axis is the one down here. Well, in physics, position is normally given with the letter x. So try not to say x-axis. Maybe we should say horizontal axis and vertical axis. That might be better. But in this case, position is going to be using the letter x. Time is using the letter t. So here's the analysis. This is linear. Position is x, time is t, just defining them. Position is proportional to the square of time. The thing that relates any proportional values is some constant. There's not going to be a plus b. Comes out of the origin. So you got to figure out the constant, the slope. So change in x over change in t squared. Now this was a computer that did this, but if you were going to figure out the slope yourself, all you have to do is pick any 2 points that are actually on the line. If it's a proportional graph like this, always make the origin one of your points. It's just easy to have 0, 0 be one of your points. I like to take a spot where the line crosses through the grid so that it's easy to read. So if you were to take your rise, in this case it would be from 0 up to 180 centimeters. And your run would be 60 seconds squared. Check out the units. These are seconds squared. 180 over 60 is 3 centimeters per second squared. This is the slope of this graph. That's how the computer got it. Putting that slope in, you have position equals the slope times time squared. Checking it. I should be able to take any time value, stick it into this, and get the right position out. So if I take 6 seconds, for instance, x equals my slope times 6 seconds. Now it's t squared, so my 6 seconds is getting squared. 6 squared is 36, times 6 is right around there. Or I'm sorry, times 3, not 6. Right around there. About 108. Look at the units. Seconds squared, seconds squared. What's left? Pretty good. Nice check for yourself. Okay, I can go through this one a little quicker because it's like a mirror image of the other one. You might get a relationship like this. In this case, this axis is increasing more quickly than this axis. So you can't write an equation. This isn't a line yet. But if we wanted to make a test plot and maybe make a linear graph to plot an equation from, what we could do is take everything on this axis and, since they're not keeping up, square them. The periods weren't keeping up. Square them. Make a new column. Period squared. Period was in seconds. Here it's seconds squared. All these values squared are these values. Once you have a line, you can write an equation. Same process, same song and dance. Define the variables. A period is a time, so they're using a capital T. You can really call it whatever you want, as long as it kind of makes sense. Length, they're using a capital L. This is a statement saying your period squared graph is proportional to the length. It's a line coming from the origin. So t squared, the period squared, must be equal to the slope times the length. There's no plus b here. Find the slope. Like I said, if it's a proportional graph, do yourself a favor. Make that one of your slope calculation points. And find another easy to read point that's actually on your line, wherever that might be. This is kind of a sorry looking graph. It doesn't have a whole lot of grid lines on it, but you have better graph paper that you've been graphing on. So pick any other point that's actually on this line. It could be that one. It does not have to be a measured point. Find the rise. That would be your change in, period squared. Find your run. That would be your change in length. Divide them out. Look at the units. Period squared is seconds squared. Length is centimeters. So your slope is going to be, in this case, 0.041 seconds squared per centimeter. So the final equation is t squared equals our slope, that's our slope, times L. And once again, you could check. Now, if you put in an L, it would be in centimeters. These centimeters would cancel with that centimeter, leaving you with seconds squared. So let's try one of those out. I'll take the highest one, 80. So t squared equals 0.0 seconds squared per centimeter times L. T squared equals 0.041 seconds squared per centimeter times 80 centimeters. Cancel the units. And I get t squared equals 3.28 seconds squared. Therefore, t must be the square root of that, which is about, according to my calculator, 1.81. Look at the units. Square root of seconds squared would be seconds. Matches up pretty closely. Must have done a good job. Now the last guy here, sorry to make this a long video, but is what it is. Inverse relationships. Inverse relationships are kind of funky because as one variable gets bigger, the other one actually gets smaller. So in this case, they're talking about waves. So wavelength and frequency. Frequency is like how fast a wave repeats itself. And wavelength is, how long the wave is. If you think back to your maybe your Algebra 2 class, you might have done some stuff with waves. So that'd be like a wavelength, right? And how quickly this thing repeats itself as time goes on, that's the frequency. Regardless, this is just an example. So what this is saying is as the frequency values get larger, the wavelength values get smaller. And I don't think it even says it in here, but a neat thing about inverse relationships, if it truly is an inverse relationship, you're going to notice that if you multiply any two of the values, you're always going to get a constant value. Let me show you what I mean here. 10 times 1.98 would be 19.8. 20 times 1.01 would be 20.2. 30 times 0.68. 20.4. You're going to notice anytime you multiply these, you're going to get right around 20. Okay? So that's indicative of any inverse relationship. So if you think you might have one, that's a good way to check it. Obviously, not linear. So we can't write an equation for it right off the bat. Since this axis actually gets larger as this one gets smaller, a way to possibly linearize this is to take all of the values that are on your horizontal axis and take their inverses, or their reciprocals, I guess you could say. So this new column is 1 over frequency. The frequency units were waves per second. Therefore, 1 over frequency would have units of seconds per wave. All they did was flip the units. 1 over 10 would give you 0.1. 1 over 20 would give you 0.05. 1 over 30 would give you 0.033, repeating, so on and so forth. So wavelength versus frequency was not a linear graph. Maybe wavelength versus 1 over frequency will be linear. I'll be darned, it is. So once you have a linear graph, what can you do? Write an equation. This one's coming out of the origin, so we can say this. Wavelength, W, is directly proportional to 1 over the frequency. And they're not using a capital F. I shouldn't either. 1 over the frequency. Direct proportion. Anytime you have a direct proportion, you can relate them with a constant, a slope. There is no plus b. Same thing, find your slope by taking the rise over run. This would be the rise. So pick any 2 points on here. Easy one, easy one. This would be the change in, and this would be the change in, not frequency, but change in 1 over frequency. Okay. Got to do your slope, your slope with units, so meters per wave over seconds per wave. These are tricky to do sometimes. You're dividing by a fraction here, so meters per wave times wave per second. Remember, if you're going to divide by a fraction, you got to flip it. So wave actually cancels here. You actually get units of meters per second on this slope. So 19.8 meters per second. So your final equation is W equals the slope times 1 over F. Look at this, 19.8. Remember how I had told you earlier that if you truly have an inverse relationship, multiplying the two values is going to give you a constant number? There's our constant number. And it makes sense because if I were to take this equation and multiply each side by F, it would end up saying F times W equals 19.8 meters per second, which means any of the frequencies times the wavelength should give you the same constant value. So where do you go with this? These are the only relationships you're going to see this entire year in physics. Everything that we ever do, every lab where we do, where I say, hey, what is the relationship, if any, between this and this? You're going to start by gathering data. You graph the data, do a good job graphing. Remember, garbage in, garbage out. If you take bad data, you're never going to get a good relationship out of it. Once you have a graph, if it's linear, awesome. Write an equation. If it's not linear, if it looks like this or this or this, you have to linearize it. You have to figure out how to manipulate one of the axes to actually make a linear graph come out of this with a test plot. And this is a nice little guide for you here. You know, modification required to linearize it. Those are already linear, no modification. So what if you get this? Well, graph y versus the square of x. These x's aren't keeping up with these y's, so square them and replot. Graph y squared versus x. These y's aren't keeping up with the x's. Square them. There you go. What if it looks like this? Maybe plot y versus the inverse of x, or the reciprocal of x. And then write an equation. Hope this helps.